Today, what I wanted to talk about was measuring position and velocity using discrete encoders. These are very, very common. They're used. It's a good sensor. They're relatively inexpensive. They can become quite expensive when you get into very high resolutions and stuff like that. But we'll talk about that. Now, this all sort of starts with discrete measurement of wheel rotation. So I believe that this was discovered by the ancient Greeks. So if I have a wheel, as I show down here, if I have a wheel, I can put a mark on the wheel and then measure the circumference of the wheel. And every time the mark goes by at the end, I take the number of rotations times the circumference, and I get the distance traveled. This method was originally called hodometry with an H on the front, but it was shortened to odometry by the same group of people that changed opossum to possum, and those would be the Americans. Okay, so obviously, if I added I do ask a question up here is what's the major source of error in this method? You would think maybe it was that, not going to full rotation or something like that, but you could get pretty close with that. The major source is not knowing the circumference accurately, because that's every time you rotate, you're going to accumulate that error. And this is one of the reasons why a method called dead reckoning in autonomous ground vehicles is at best suspect, because you'll never know that measurement, and things change. Tire inflation, changes with temperature, the pressure, all that kind of stuff. It's just very difficult to know. Most places that do like car measurements and stuff, here's my approximation to a car. You'll see them doing tests on test tracks with that little wheel tied on the back. The reason that's there is because it's independent of the pneumatic wheels on the car, and so by putting a hard wheel on this, you can get relatively accurate measurements that where the diameter of that doesn't change very much. Okay, I could improve resolution of the system by adding more marks on the wheel. So I could put a bunch of marks on the wheel and count all of the marks, and then I would be able to more accurately determine the fraction of the circumference that was traveled and get a distance traveled, but I'm still slave to that circumference measurement. Okay, so modern encoders typically use they use a wheel, but there's a mark or target that passes in front of some emitter detector pair, or and so in one case, there's one style, I will have an opaque section and then clear sections, and I'll be able to tell when one of these pieces has passed, because it will go from the emitter detector pair seeing the emitter on one side and then not and then seeing. And so as I go around, as I'm rotating around, I will see the rotation as it goes along. I can also do this with magnetics, and in the case of magnetic, I may have a tooth wheel and some sort of reluctance sensor down here, and as the tooth comes around, the sensor will put out a little spike for each tooth. Okay, optical sensors typically consist of a light emitting diode and some kind of photodetector. Photodetectors can be photodiodes or phototransistors, and the magnetic detector is some sort of reluctance change that you're going to detect. Or if it's an actual magnet, you might get a actual generated voltage from a coil. Okay, if you've ever been into older small gasoline engines, they use a similar method with magnets on the flywheel going past the coil to generate the spark. Okay, both detectors produce or can be made to produce a square wave signal. So I get light and dark and light and dark. as I'm going along as it's rotating. And the wheel position can be determined by counting the number of dark to light transitions the detector sees. Now, it works good, and great is what I say, unless you change directions. If you change directions, then you no longer know which way you're going. So if I have a wheel and it's rotating in this way, and I've accumulated, say, n counts of the pulses, and then I go back this way, the first pulse is C, it will tell me I'm at n+1, so implying that I've moved further down here rather than moving back. And so that's an issue since I have no information on direction. So I can fix this by adding another detector emitter pair that is offset from the first pair. And so adding the new pair, so the output waveforms that I produce are 90 degrees out of phase, and this is called quadrature measurement. And so I'm able to detect the changes, and in this case the output waveforms look like this. So if I were consistently rotating sensor 1, could look like this as it sees its transitions. Sensor 2 seeing the same transitions, but you'll notice that sensor 2 is leading. Its transitions occur before the transitions on sensor 1. And so sensor 1 the transition will occur later, and it's 90 degrees out of phase. Okay, so I show down here that this is the waveforms I would get if I was moving in one direction. Okay, sensor 2 is leading, and that means that sensor 2's transitions occur first. It leads sensor 1. Okay, if I stopped, then I would stay at the state I was at until I started moving again. But let's say that I stopped and then I reversed. So now if I reverse, what's going to happen is now sensor 1's transitions occur first, and sensor 2's transitions occur later. So now sensor 1 leads sensor 2. And so by knowing the transitions, or counting the transitions for both sensors, and knowing which sensor transitions first, gives me position and direction information. And from that, if I count that, by looking at that, I can get accurate position information, because I will know exactly what direction was turning when the transition occurred, and so I know where I am exactly. Okay. Also, you can do a trick, and instead of just counting, these are for the mechanicals and hopefully not the electricals. Transitions here are called leading edges. Okay, if I count both the leading and trailing edges, and for both sensors, so I've got the other sensor doing something like this, and I count that one, and I count that one, and I count that one, then I can get 4 times the resolution out of this, and that's called quadrature, also quadrature measurement. So I resolve the position to 4 times the number of light-dark transitions on the wheel. And so if I had a system that had 1024 marks on the wheel, and I have one of these in my office, if I use quadrature, I'll get 4096 basically ticks per revolution, which is a pretty accurate. It's a sub-tenth of a degree measurement, and so it's pretty accurate. It's not as accurate as LVDTs or RVDTs or resolvers, but it's pretty accurate. Okay, decoding the waveforms into usable position data used to take some skill. You had to be able to design circuits that could detect what was leading, what was trailing, all that kind of stuff. However, you live in a golden age. Almost all modern microcontrollers have this function built into their timer counter suite. You can find it in there somewhere, or somebody's written code for it. Or you can also buy standalone integrated circuits that do the same thing for you. This is one example. It costs $4.12. You hook up the encoder and it decodes it for you. Now the type of encoder I've been describing in this is called an incremental encoder. And when it's powered on, it can only determine incremental position changes from where it is. And in short, what I say here is it wakes up stupid. Okay, it does not know where it is. It does not in any absolute sense. And so from there, that's zero for it. As soon as it's turned on, that's zero. Okay, I've mentioned before your printer uses an incremental encoder, but it moves the print head to a known position. That's why you hear that awful grinding noise when you first turn on your printer, because it's sliding the print head over against the stop, and it holds it there long enough so if I had to travel the entire distance along the carriage of the printer, it holds it there long enough to it knows it reaches that stop. So that said, your printer also has a Mylar tape with stripes on it, so you can do linear and rotary sensors and very accurately determine something's position. Now, you may ask at this point, are there non-incremental absolute optical sensors? Yes, but they come with their own set of problems, and so we'll talk about that a little next. Absolute optical encoders. So if I added some more emitter detector pairs, so in this case I'm going to add 3, and then each one's going to have its own ring. Okay, and so the emitter detector pairs will detect that. And I just decided to naively use a binary code on my ring. So I've got, if you look here, I've got 0, 0, 0, 0 here, or sorry, I'm going to count this way, 0, 0, 0, 0, 0, 1. Okay, so things are going pretty good here. I have 1 bit change. Then I go to 0, 1, 0, but this is not good because I've got 2 bit changes. So this bit changes and that bit changes. Okay, I go over and I do this one, the same thing again. I've got 1 bit change there. I had made a mistake there. Anyway, I have 1 bit change there. But then I go to this really bad one here. It's 0, 1, 1, and then I change it to 1, 0, 0. So 0, 1, 1 changed to 1, 0, 0, and I have 3 bit changes. Okay, now what could possibly be the problem? Well, let's say that when you're rotating this, since the world is not a perfect place, I end up with a sensor that sits right there. Okay, it's sort of on the border between 0 and 1. Let's say that just for happiness sake, that these two, I'm going to make them solid so they won't get confused with zeros. These two have transitioned completely. But this one's kind of sitting on the edge. So now, looking at it, it's either going to think it's at 1, 0, 0 or 0, 0, 0. Okay, so that means that it's either going to think it's right here, where it's supposed to be, or it's going to think it's over here, 90 degrees opposite to that. And that is very bad, okay, because the nature of these, if I'm sitting right on a light-dark border, my circuitry is likely to select a state, but either that or it's just going to dither back and forth through that state. And so my position measurement would be jumping between these two all of the time. Okay, so that's bad. So what can we do? We can change the code. Okay, what we're going to use is a binary code that has a guaranteed 1-bit change, and this is called a gray code. Okay, so instead of using the one I had there originally, my outer ring now consists of around like that, which is this. And you'll notice that my next ring is designed such that I only change 1 bit. Okay, so I change 1 bit there. I go to the next one and I only change that bit. I go to the next one. I've done 0, 1, 0. I go to 1, 1, 0. Okay, so 0, 1, 0. Yeah, 0, 1, 1. Anyway, and in this case, I'm only going to change that bit. Okay, so by only changing 1 bit at a time, I guarantee that if I'm stuck in a similar measuring position with this bit dithering, this one and these two fixed, let's say that they're fixed to where they're supposed to be, then the only thing that will happen is I will move between these two adjacent positions. So my measurement might be jumping back and forth between those two adjacent positions, but it's not going 90 degrees over to the other side of the encoder and then back and forth. Okay, so a non-switching bit or a bit toggling back and forth. Now, why don't we just use these? Why don't we abandon those nasty incrementals? Lots of sensors for high resolution. And it's not that optical sensors aren't cheap, they generally are. But if I wanted to do like a 16-bit grade code encoder, oh goodness, I would end up with a very large disk. Okay, lots of disk. And then they're expensive in manufacture, and generally the manufacturers will pass that price on to you. So that's the reason why absolute optical encoders are more rare, and they generally have less resolution than an incremental encoder. Now you'll go, are there hybrids? Yeah, there are some attempts at hybrids of incremental and optical, but in general, it's going to be, you're going to use an incremental unless you have a desperate need for absolute optical. Now, you could replace absolute optical with RVDT or even a potentiometer, and it would be much cheaper than going this route. But if you really need optical, you can find them. Okay, I want to also talk about measuring speed with incremental encoders. There's a couple of methods in which you can use. The first one is called pulse counting. So the encoder, as it's rotating, produces a pulse train like this, and then I just measure over some time t, and I determine how many pulses occurred in that. Okay, so the angular speed in radians is given by this radians per pulse divided by the total time divided by the total number of pulses. And when I write this out, I've got 2 pi n over nt. And so if I did this in quadrature, or even if so I had 2 sensors, I could replace this by 4n, and so I would get an even greater resolution, angular speed resolution. But let's check and see what the resolution is. So I'm looking at 2 adjacent counts. So right here, when I do the math, it comes out to be that. Okay, unsurprisingly, the bigger n you have, in other words, the more marks you have on your encoder, and the longer the time sample window is, this measurement window, the better your frequency resolution is going to be. Now, the resolution is the same for all velocities. It's independent of how fast you're rotating. But as a function of measured velocities, I get this ratio here, and it gets smaller, so I get many more counts for for higher velocities, and this gets smaller for higher velocities. So that means that in time t, if I'm going really fast, then I get a lot of counts in that window t. And if I'm going really slow, what that means is I get very few counts in that window t. And so this kind of leads us to some conclusions. The pulse counting method is effective at higher speeds. And it's easy to implement on a modern microcontroller. It's something that you can find quite easily and quickly, hook up an encoder, and off you go. Okay. Method 2 is called the time between pulses. And in this case, my transitions are shown here, and then I count with an independent clock, m cycles. So this transition occurs, I count, 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 and then it goes the other direction. And I stop counting and I do the calculation. In this case, this is the resolution, 2 pi divided by the number of marks. And then this is the cycles counted divided by the frequency of the independent clock. And when I write it, I get 2 pi f over nm. Now I want to know resolution, so I take a look at the 2 adjacent samples so I can determine velocity measurements, so I can determine what kind of resolution I can get. When I do this, this has this nasty m times m minus 1, but if m is large, the total number of cycles is large, I can reduce this to this. I can substitute in from the previous equations, this one right here, solve this for m squared, and I end up with this as an approximate value for the frequency resolution. So you'll notice that if things start to move really, really fast, what that means is these transitions would be occurring really quickly. I wouldn't have time to count very much in between each of those transitions. And so so that's for big omega, and it's proportional to omega squared. And but for high frequency clocks, the clock frequency, this independent clock has frequency f. For independent clock, if they go to higher frequencies, I get better resolution. And that naturally makes sense, because if I have many, many more transitions than I'm shown here, I could resolve this into a pretty fine resolution for velocity measurement. Okay, conclusions on this is the time between pulses method is good for slower speeds, and things get better the bigger the frequency of the independent clock f is. Now there are devices you can find now in some microprocessors that do this. You can find code that will simultaneously do both. So we'll measure both, and then you get to choose which one's better. So you'll get an approximation to velocity from one, and then you'll go, well, I'm in the low range, I'm going to use this measurement instead. And so so both of them occur. And just in finishing this up, analog velocity measurement, we did that in the lab in 5310. Even though you're not aware of it, we were driving a DC motor as a generator, and that DC motor is a tachometer in that case, and so it's generating a voltage that's proportional to the angular velocity that you're turning this shaft. Almost all analog velocity measurements are based on this V equals N d phi dt, time rate of change in magnetic field, number of turns on a coil, and that's going to give me voltage. Now, you may ask the question, why don't I simply differentiate a position measurement? So I take, I've got some position measurement, and I do a derivative, and I get a velocity. Well, the problem is if I sketch briefly the Bode plot, the Bode plot of a differentiator looks like this. And so this is omega, and this is dB gain. And as I go higher and higher in frequency, the value gets bigger and bigger. And so any noise that occurs in an environment will be amplified by differentiation. So as you're measuring something in position, you will amplify every change, and it will get bigger and bigger and bigger. And any measurement noise that happens to occur will be amplified by the differentiation procedure. That's how you use encoders to measure position and velocity. I'll see you in a